All right, so this video is going to show you how to do a mole-to-mole problem. And before we actually go into this particular problem, I want to look back at a problem that will sort of hopefully help you to understand this. So here's a problem which you probably already have the answer to in your head, but let's just look at how we would solve this using the same type of analysis. So how many tricycles can you make with 27 wheels? So what we need is an equation for the process of making tricycles. And in this case, the equation is we need 3 wheels plus 1 frame, and that is going to make us 1 tricycle. Notice the formula for a tricycle is something that has 3 wheels and 1 frame. So how do we go about this? Well, the way we did this, the way you probably already did it in your head, is somehow we had to make the connection that it took 3 wheels to make 1 tricycle. We can actually write a conversion factor for that. We can say that 3 wheels makes 1 tricycle. That is the connection between the two. And we're going to ignore the frames in this case. We know that we're going to need frames for it. But what can we do with this information? Well, if we have 27 wheels and we have this conversion factor here, we can do a dimensional analysis, a fence post problem with this. We say that every 3 wheels makes 1 tricycle. And we can set that up and do it like a regular conversion. Wheels cancel, and we end up with, as you already probably knew, 9 tricycles. So this is just a conversion problem. Stoichiometry problems are really just conversions. In this case, we're converting from one substance to another, and we need to simply know what the conversion rate between them is. We get that from these numbers out front called the coefficients. They might say, well, don't you also need 9 frames to make these tricycles? And yes, we do. That's usually understood. We have 27 wheels, and we make the assumption that there's plenty of frames available to make these tricycles. Now back to the application of chemistry. Here's a problem. They want to know how many moles of NH3 can I make with 48 moles of hydrogen. So this is pretty much the same type of problem. We have hydrogen, and we're trying to figure out how much NH3 we can make from it. And we're going to assume that we have plenty of N2 available. Sometimes it'll actually say that in the problem. But what is the connection between H2 and N2? The connection is that every 3 moles of H2 is capable of making 2 moles of NH3. You might be wondering where to get this moles from. In a chemical equation, these numbers here, they can either mean individual molecules or they can mean moles. So either way, your choice, we're usually going to refer to them as moles. So another way of reading this equation is that 1 mole of N2 and 3 moles of H2 together are capable of making 2 moles of NH3. But all we really need out of this is this fact that 3 moles of H2 can make 2 moles of NH3. So now how do we do this problem? Well, we were told we had 48 moles of H2 to start with. So that's what I'm going to start with. And I'm going to set it up as a fence posting problem. I'm trying to get from moles of H2 to moles of NH3. So I set up my fence post. Down here, I'm going to need moles of H2. And according to my thing up here, that's going to be 3. This is going to be 2 moles of NH3. And I'm just going to multiply this out. 48 times 2 divided by 3. And that should give me 32 moles of NH3. Because the moles of H2 cancel. So, assuming there's plenty of nitrogen, 48 moles of H2 will make 32 moles of NH3. And this should also make sense, because what this equation says is that every 3 H2 that go in, 2 NH3 come out. So we would expect less at the end. You know, if I had something that took in $3 and gave me 2 back, when I put in 48, I would expect less to come out as a result. So that is a mole-to-mole stoichiometry problem. It's a one-step problem in which you use the coefficients in the equation. You just make a connection between the chemical you're in to the chemical you're going to. So anyway, until next time, I am Derek Genova. Have a delightful day.